Hi, I'm Craig the Geologist. What are the laws of geology? And are we allowed to break those laws? Come join me. The first four laws of geology are often referred to as Steno's laws. These are named after Nicholas Steno, a Danish scientist in 1669. And these are the early days of modern science. And so these laws are not very complex. In fact, they're based pretty much on common sense and what we today consider grade school level physics. But don't let that trick you into thinking Nicholas Steno was a bit of a dunce or anything. He was not. He also came up with the first law of crystallography, which was a very complex observation, which we're not going into today. But let's go into Steno's laws first. Steno's first law is the law of superposition. The law of superposition states that for sedimentary rocks and extrusive igneous rocks, the youngest rocks will be found at the top and the oldest rocks will be found at the bottom. Now, this is a pretty intuitive thing if you think about it. In all sedimentary systems, the sediments are deposited from above. You don't have sediments rising from the depth. And so regardless of whether it's being deposited in an ocean or in a stream system, the layers are going to be laid one on top of the other like so. Same goes for extrusive igneous rocks. If there's a lava flow, it's going to come out like this. It's not going to make its way underground. Now there are intrusive magmas. This is why we said this applies to sedimentary rocks and extrusive rocks. Anything that's erupted out or that comes out sedimentarily will follow the law of superposition. So if our units are A, B, C, D, and star, because I forgot to letter that one, star is going to be the youngest. A is going to be the next youngest. B, C, D is going to be the oldest. The law of superposition. Pretty intuitive, really. Now, can the law of superposition be violated? Can we break the law of superposition? And the answer is yes, with a big asterisk on it. Yes, only if something very complex has happened tectonically. So what you can get are units. I'm going to use different colors to make it a little bit more obvious. We'll make the bottom unit blue and the next one red, and the next one green, like so. All right. So if you have, say, a mountain building event or something like that happening, the units can end up being squished and folded. And so, accordion style, as you squish these rock units together, they have to kind of fold. And so you will end up with units that, instead of looking like that, will look like okay. So now we've folded our rock units. This is an anticline. This is a syncline. That's just referring to the kind of the direction of the hummocks. But we haven't violated the laws of superposition yet. All right. If this is unit A and B and C and D here, well, you can still see the youngest is at the top, oldest is at the bottom. Everywhere you go, straight down. However, we can get more complex folding than that. And things can be folded multiple times in different ways. You can have pretty much every imaginable type of 3D structure down below, and you can get tilted folds, things that can look more like this. Like this. Now, is the law of superposition violated? Well, if you look on a large scale, and this is still A, B, C, and D here, the answer is no. However, if you've got erosion going on, we'll say this is our ground surface up here. And let's say there's a cliff. Say we got like the Grand Canyon or something here. Now a geologist comes and they take a look at these rock units. They say, well, this is strange. We've got C up here, and then B right here, and then A, and then B, and then C, and then D. These rock units are all out of place. Well, a geologist then takes a look at the larger scale and says, hey, there's something structurally going on here that's very complex. And a creationist takes a look at that and says, ha, geology doesn't work. However, this is how the law of superposition is sometimes violated. In this spot right here, the units are out of order because of the folding. However, the law of superposition still does technically hold because the units on top, absent the folding, are still in the order in which they were deposited. All right, Steno's second law is the law of original horizontality. That's also pretty straightforward. Referring to sedimentary rocks and extrusive igneous rocks again, it states that rocks were originally laid down in a horizontal manner. That is, the original orientation for the sandstones and the limestones was all like this. So, if you're at a place that does have wild folding going on, Steno's law says, hey, they weren't deposited like that. You're not seeing like preserved hills and valleys. It was all originally deposited horizontally, and this is something that happened after the fact. That law holds true today. However, can that law be violated? The answer is yes, but only kind of. In some places, we see deposits that are associated with landslides, that are associated with erosion from mountainsides. And so we do know that in some places, for example, out at the Rocky Mountains today, deposits will slope down naturally following the shape of the mountains that shed the material. But the law is really only ever violated by a couple of degrees. It's not violated massively. If you ever see a rock unit that is vertical, and that can happen sometimes based on what's happening tectonically, that rock unit was not deposited vertically. It was deposited horizontally or very close to horizontally and then tilted to its current position. Steno's third law, the principle of lateral continuity. This one sounds a little complex, and then when you sketch it out, you realize how very, very simple it is. But it states that if you have a rock unit in one place, and then a big gap, and an identical looking rock unit in the same position on the other side of that gap, they are probably the same rock unit. All right, so if we do our rock units here, and we have a valley in between, the principle of lateral continuity says that on either side of the valley or road cut or whatever you're encountering, if this unit looks a lot like that unit, they are probably the same unit. That seems incredibly intuitive to us, but to the naturalists of the 1500s and early 1600s, it wasn't obvious. And so Steno basically had to spell this out and say, hey, if unit A here looks like unit B right there, they were probably originally connected before the valley was eroded out. And if you recall that in the 14, 15, and 1600s, a lot of naturalists were young earth creationists because the church ruled the day. It was not obvious that this valley hadn't been there since the creation of the Earth just a couple of thousand years ago. And so it was important for Steno to say, hey, you know what? These units were originally laid down as a single unit, and the valley came later. This valley cuts through them. And that takes us to our law of cross-cutting relationships. The law or principle of cross-cutting relationships says that if one rock unit or one geologic feature cuts through another, the one that cuts through is the younger feature or rock unit. If that feels complex, it'll feel a lot less complex and a lot more intuitive once I sketch it out. So if we have rock units here, and a dike cuts through them. And let's add one more rock unit on the top here. All right, so we have a magmatic dike here that cuts through these rock units. Obviously, the magmatic dike has to be younger than these rock units. Why is that obvious? Well, those rock units have to be there for it to cut through them. It can't cut through things that don't exist, right? That should feel pretty intuitive. However, take a look at this top unit. This top unit cuts through the dike. And so we know that this top unit is younger than the dike. If it was older than the dike would have cut through it on its way to the surface. This unit here came after the dike. So the cross-cutting relationship tells us that we'll call this A, B, and we'll call these C through D, E, F, C through F down here. We know that A is younger than B, and B is younger than C through F. And we can use this in very complex situations. All right, what I've got here is a complex mess. Let's label it so we can talk about it. All right, so we have units A, B, C, D, E, and F over here. These are going to be our sedimentary rocks. We have a fault cutting through them. We labeled that fault H. We have a poorly labeled unit of granite here, G, and a dike, I, cutting through it. What are the relative ages of these rocks? So based on the law of superposition, we know that A is younger than B, is younger than C, younger than D, younger than E, younger than F. So we know that F, put this in here in terms of ages, F is older than E, which is older than D, which is older than C, which is older than B, which is older than A. Okay, great. That was obvious based on the law of superposition. But how old is H, the fault that cuts through these units here? Well, H must be younger than anything it cuts through. So H is younger than F, younger than E, D, and C, but it does not cut through B. So we know that it is older than C, but younger than B. So let's squeeze our fault H in here. Now, how about our granite, G? Well, we know that it has to be younger than F because it cuts through F, but it has to be older than H because The fault cuts through it, so the fault must be younger than the granite. We don't know exactly how old our G unit granite is, but we know that it's somewhere between F and H. So it's somewhere in the EDC range of ages. And you could do radiometric testing or something to determine the age more exactly, but we can do relative dating this way. And how about I? How old is I? The dike that cuts through all of this? Well, it cuts through FEDCB and gets part of the way through A. So we know that it is about the same age as A. This is the law of cross-cutting relationships. Now, can this law be violated? Kind of, yes and no. At the surface, pretty much never. I don't know of a way you could get a pre-existing solid rock to inject between things in a way that would mess this up. But it may be something that happens in the mantle. At the surface, though, where we live and observe, it's not something you have to worry about. So those are Steno's 4 laws of geology. But what else have we got? Well, one commonly cited law of geology is uniformitarianism, the principle of uniformitarianism. And that basically states that the processes that are happening today are the processes that happened in the past. You can look at the modern day and extrapolate to the past. Well, there are limits to that. That law is violated more often than most of the other laws because conditions millions and even billions of years ago were not always the same as they are today. For example, banded iron formations. North of where I live, there are enormous banded iron formations. But banded iron formations haven't been laid down in the past several 100 million years. And in fact, almost all of the banded iron formations on the planet were laid down more than 1 billion years ago. And the reason for that is that today the conditions don't exist that would allow banded iron formations to be deposited. The oceans have a different chemistry. The atmosphere has way too much oxygen in it. There's too much photosynthetic life. It can't happen. So there are limits to the uniformitarian argument. But it does hold insofar as you can't invoke magical processes that can't happen today. You know, the conditions may have been different in the past, but the basic science and chemistry and the laws that govern them were the same. You can't say, okay, these banded iron formations came from radioactive space squirrels. You have to cite something that you can observe today that might have happened in the past that isn't happening now. The law of inclusions isn't too wildly different from the law of cross-cutting relationships. It states that if you have a mineral inclusion inside the grain of a rock or inside igneous rock or something, that inclusion must be older than the rock that it's included in. And when this law isn't observed or followed, when you're not paying attention to that law, it can really mess things up. For example, there was a case where people were trying to do radiometric dating of some sandstones. Now, if you've seen my bit on radiometric dating, you know that you can't radiometrically date most sedimentary rocks. And so that should already be raising red flags. But there were zircon grains locked inside the sands of these sandstones. And all the evidence and the relative dating has shown that these sandstones must be about 5 million years old. But when they did the zircon testing on it, it turns out that the sand in the sandstone was about 2.5 billion years old. That's a big discrepancy. 5 million, 2.5 billion? What's going on? Well, the zircon crystals that were locked in the sand grains were a lot older than the grains of sand. The sand in the sandstone eroded out of a mountainside, and the rocks that mountain was made out of were 2.5 billion years old. But they only eroded around 5 million years before the testing was done. And so when they radiometrically tested the zircon in these sand grains, it gave them the age of the original rocks it came from. The inclusions were far older than the grains of sand. Inclusions always older than the rock that includes them. Now, In order to apply that, you need to be able to know the difference, for example, between a phenocryst and an amygdala. There are cases where you can get confused, but in all cases of an inclusion or a phenocryst, the crystal, the mineral, the rock, whatever it is that's being included, is older than the host. Finally, the law of faunal succession states that organisms tend to progress through the rock units in a predictable way. And generally speaking, they become more complex. When the principle was first proposed, it was a very basic, things get more complex as you get to the younger rocks. Now that we've mapped out so many extinct life forms, we know exactly what periods of time different organisms thrived through history, and we can map that out in a very predictable way. But the law or principle of faunal succession basically says that the fossils will tell you the age of the rock, in a sense. If you've got trilobites here, and the trilobites were common from 600 million years ago to 300 million years ago, don't quote me on those ages because I'm pretty sure they're both wrong. Then you know that your rock unit is between 300 and 600 million years old. And if you can narrow down the type of trilobite to one that only existed between 310 and 300 million years ago, and you found that, well, then your rock is 310 to 300 million years old, unless you do a more complex dating system and you come up with a new age for the trilobites maybe. But if you're not doing that, you can just use the law of faunal succession to figure out relatively how old your rock units are. These are the guiding principles of geology, of earth science, of our natural world. Without these principles, if these principles didn't exist, everything would be incredibly chaotic. Nothing would really make sense. I mean, think about it. If you didn't have the law of original horizontality and, vertical rock units were just being glued on like a kid with a glue stick or something, how could you understand anything that was happening in the world? If you didn't have the law of superposition, if random rock units were random ages, nothing would make any sense. So these principles are using basically common sense and very simple principles of physics to explain the world around us and allow us to build a framework that lets us understand the earth we live on. I hope that was helpful. Please join me next time.